Hey further students, in this video we're going to be looking at bipartite graphs and allocation problems. So let's get stuck into it. Firstly, this definition of bipartite graphs, which you can kind of really read as like two-part graphs. These are graphs that involve two distinct sets of vertices, and so each vertex in one set connects to at least one vertex in the other set, but the vertices are not connected with other vertices within their set. Within their set. Sorry, that's a typo, clearly. Bipartite graphs can also be weighted or directed. So this one here is an example of a bipartite graph. You can see there's kind of a set of vertices on this side, there's another set of vertices on that side. Within their own set, so these vertices A, B, and C aren't connected to each other, but they're all connected to at least one vertex on the other side in the other set, and likewise with D, E, and F. D, E, and F aren't connected together, but they're connected to at least one other vertex in the other set. Here's an example of how a bipartite graph might be set up using an application problem. This one says, Mr. Allison refuses to teach anywhere but in room 102. Mr. Johnson is happy to teach in room 108 or room 416. Mr. Simpkin will teach in room 417 or 102. And Mrs. McKinnon is happy to teach in any of the four rooms mentioned. It's a pretty old example. Firstly, a couple of these rooms are now non-existent and one of these teachers is retired. But anyway, so what we might do is we could say, well, let's have one set of vertices represent the teachers. So we had Mr. Allison, Mr. Johnson, Mr. Simpkin, and Mrs. McKinnon. So we could give each of them a vertex just using the first letter of their name. And then the four rooms that are kind of involved in this question are room 102, room 108, room 416, and room 417. You can give each of those a vertex. And so in this case, the connection would just represent like, which teacher is able to teach in which room. So Mr. Allison doesn't teach anywhere except room 102, so we do an edge from his name to room 102. Mr. Johnson was happy to teach in room 108 or 416, so 108, 416. Mr. Simpkin was 417 or 102, so 102 or 417. And Mrs. McKinnon was happy to teach in all of them, so she can have four edges, one to each room. All right, and then you could use this graph to kind of help allocate teachers to classrooms. Maybe if you're doing the timetable for next year or something like that, you could use this to help work out which teacher should teach where. Okay, in this next section, and this is kind of the big thing to get your head around for this section, we look at how we can apply this sort of idea to allocation problems. And there's this big, scary sounding process that we use called the Hungarian algorithm. We use it to try to allocate, sometimes we allocate like people to different tasks, or we might allocate stock to certain stores or something like that. But what we're trying to do when we use this process called the Hungarian algorithm is minimize either the time or the cost. Okay, so you might be trying to get four different people to perform four different jobs, but you want to do it so that you can get all of them done as quickly as you possibly can. Or maybe it's like four different people who have to do different things to build a house, and you want to build the house with the cheapest possible cost. So you want to get the four people to do the jobs that are going to make it cost as little as possible. All right, that's the kind of thing that we're going to use the Hungarian algorithm for. The Hungarian algorithm has got these rules, these steps, and like with a lot of processes that are kind of, I guess, long-winded, sometimes you learn it better by actually going through the process a couple of times. But just to sort of skim through these steps, the first step we call row reduction. The second step is called column reduction. Third step, we're going to call it crossing out. Fourth and final step is the allocation. And then the fifth step, which is if required, you actually work out what the minimum time or minimum cost is. Now, obviously, you can pause this video or look in your own notes to kind of read through these in more detail. What I'm actually going to do is go through the examples, and I think that I can kind of explain the steps as we're going through the example, and it will make more sense. So we're going to do two examples. This is the first one. Example 2, it says 4 workers, Andrew, Brian, Christine, and Diana, are required to complete 4 different jobs. The cost of allocating each worker to a particular job is shown in the table below. So for example, when we read through this table, if we're going to get Andrew to do a job, well, for job 1, it's going to cost $30 if we get Andrew to do it. For job 2, it's going to cost $40 if we get him to do it. For job 3, $50, and so on. So this table's showing like the cost of each person doing a job. To pick another number, like it'll cost $80 if we get Diana to do job 2, just so we kind of know how we're interpreting this. And essentially the idea of this is that we're just going to give each person one job, okay? But we want to pick it so that we get the minimum possible cost. And sometimes you might just be able to do it by looking at it, but in a lot of cases, particularly if you're going to get a question on a SAC or an exam, it's actually quite difficult to just look at it and do it, and you'll have to go through this process that we're calling the Hungarian algorithm. So the first thing that you do, I'm going to use some spare paper here just because I can spread it out a little bit more. The first thing that you do is you write the information that's in your table in matrix form. Okay, so I'm going to start with this, and so we're going to say 30, 40, you might want to fast forward this, I should have done this in advance, but anyway. In fact, yes, I would definitely fast forward the sort of 20 seconds if I was watching this, if I was you. If not, I don't know. I should have played some elevator music or something. Oh, of course, now that I'm multitasking, I've written down a number wrong. Silly me. 50 and 70. So you basically just take the numbers from the table, put it into matrix form. And now we're going to go through, and I'll kind of keep flicking back and forth between the steps. This first step is row reduction. So our sort of description here is that we find the smallest value in each row, and then in each row, we subtract the smallest value, this is poorly written, from each value in the row. So start with the first row, and we find the smallest number in the first row, and in this case, it's 30. 30 is the smallest number in the first row. So in our next matrix that we create, all right, so I'm going to rewrite this new matrix underneath. We're going to take, try to keep this neat. We're going to take every value in this row, the 30, 40, 50, and 60, we're going to subtract 30 from each of those numbers. So the first number becomes 0, because 30 take away 30 is 0. Then 40 take away 30 gives us 10. 50 take away 30 gives 20. And 60 take away 30 gives us 30, right? So that's the first row done. The second row, 70, 30, 40, 70. Well, in this case, the smallest number in the second row is also 30. It's a bit of a coincidence. So we're going to take the number 30 and subtract that from each of these numbers in this second row. So 70 take away 30 gives 40. 30 take away 30 gives 0. 40 take away 30 gives 10. 70 take away 30 gives 40. All right. Third row, so let's just repeat this. We find the smallest number in the third row. This won't usually happen, but just by coincidence, this number is also a 30. So we're going to subtract 30 from every number in the third row, and that gives us 60 take away 30 is 30, 50 take away 30 is 20, 60 take away 30 is 30, and 30 take away 30 is 0. All right, last row. Smallest number in the last row is 20. Thankfully, we've got something different there. So in the last row, we're going to take 20 away from each number. So 20 take away 20 gives 0, 80 take away 20 gives 60, 50 take away 20 gives 30, and 70 take away 20 gives 50. Okay, so that's the process of row reduction. That's the first step. The next step in the process is called column reduction. And for column reduction, we basically do exactly the same thing, but we work down the columns. Okay, so we find the smallest value in each column and then subtract the smallest value from each value in that column. So we're kind of going to go to set up another matrix here. Right, and what you'll notice is that in some of the columns, because of what we did in row reduction, in some of the columns you're already going to have a 0. So basically in the columns that already have a 0, nothing's going to happen, because if I go to this first column here and I say, oh, I'm going to subtract 0 from each number, well, subtracting 0 doesn't change the number. So for the first column, I'm still going to have 0, 40, 30, and 0. For the second column, well, again, the smallest numbers are 0, so subtracting 0 doesn't do anything, and I get 10, 0, 20, and 60. In this third column, this is where something actually will happen, because the smallest number in the third column is a 10. And so what I have to do is subtract 10 from each of these numbers. So 20 take away 10 gives me 10. 10 take away 10 gives 0. 30 take away 10 gives 20. And 30 take away 10 gives 20. Okay, so this third column did actually change. And the last column also has a 0 in it. So when we subtract 0 from each number, we're just getting the same number again. And so the fourth column, the numbers aren't changing either. So we've kind of done here, as we've kind of made our way through, we've done row reduction. This step was column reduction. Okay, and this is the matrix that we currently have. Now, going back to our steps, we're now up to this crossing out step. Okay, and the crossing out step says that what we're going to do is we're going to cross out all the zeros in the matrix using the minimum number of vertical and horizontal lines. So the idea here, and this zeros are very important in this process, is that we're going to try to cross out all of the zeros in the matrix using as few lines as possible. And they have to be vertical or horizontal lines. So what you'd aim to do is actually cross out as many zeros in one line as you can. So for example, I can see that I've got 2 zeros here in the same row. So I'm going to go and cross out sort of that way, right? Because that wipes out 2 zeros. I'm trying to do this using as few lines as possible. I've got 2 zeros in this first column, so I might cross out like that, right? And I've also got a 0 over here in this this last column. Now I could cross it out a couple of different ways. It doesn't really matter which way I go. Just for the sake of it, I'm going to go like that. Okay, and so in that crossing out step, there were 3 lines required in order to cross them out. So when we come back to this crossing out step, if the number of lines is equal to the number of tasks, then stop. And so in this question, we've got 4 tasks to allocate. We've got 4 people and 4 tasks. Remember, it's a 4x4 matrix, so that reminds us there's 4 of them. So basically, what we have to do, excuse my dog, really sorry, is we actually have to keep going, because we were able to cross it out with 3 lines instead of 4. Apologies for that, I just had to get my dog to quiet down. So as we said, we've just done this crossing out step, and we've been able to cross out all the zeros using just 3 lines. So when we come back to what the crossing out step says, it says that we can stop if the number of lines is equal to the number of tasks, but if not, then we have to find, so this is what we're going to go to next, find the smallest uncovered number and subtract it from each uncovered value and add it to any elements at the intersections of lines. Okay, that sounds complicated. Let's just explain that as we go. So what we're going to do is, using the matrix that we have with our crossed out lines there, we're going to find the smallest number that's not covered by one of these lines. And in this case, that's a 10. All right, so that's our smallest uncovered number. And what we're going to do is we're going to subtract that number from all of the other, or from all of the uncovered numbers. So basically our new matrix is going to become, try to move this for you guys to see it properly. So our next matrix, start with these uncovered numbers. We're going to take away 10 from all of them. So this is going to become a 0. This 10 here is going to become a 0. These 20s are going to become 10, because we're doing 20 take away 10. We're subtracting 10. So get a 10 there, a 10 there, and a 10 there. And this 60, when I subtract 10 from it, will become 50. Okay, so that takes care of all the uncovered numbers. Then we take the numbers at the intersections, which is this 40 and this 40, and we actually add that 10 to these intersections. Okay, so those 40s will become 50s. All right, and everything else that was covered up just stays the same. So this 0 stays as 0, this 30 stays as 30, these 2 zeros here stay as zeros, and so on. So we've got a 30 and a 0 going down that first column, and a 0 and a 50 to complete it all. Okay, so now what we do is we just try this crossing out step again, okay? And we try to cross out all the zeros using as few lines as possible. So let's try it again. I can wipe out 3 zeros with 1 line, so that would probably be the best way to start. All right, I can wipe out these 2 zeros in 1 line in the next sort of row, so that looks like a good one to do next. And you can see with these 2 remaining zeros, no matter which way I go, I'm going to need 2 more lines to cross them out, right? I can't cross them out using just 1 line. And so I can try going, you know, like that, and then like that. I could have tried going across, but the point is that that took 4 lines. There was no way I could do that with any fewer than 4 lines. So 4 lines were required to cross out there, and that's great. That actually means that we're finished the matrix steps. Okay, so at the end of this crossing out, it said repeat step 3 until number of lines equals the number of tasks, and it did. We have 4 tasks, and it took 4 lines. So now we get to this final step, and this final step is the allocation, where we actually choose who's going to do what task. And so the way it works, and the zeros are really key here, we choose 1 0 per line so that each task is allocated to a different person. And we can draw a bipartite graph to help us here. We don't have to, but we can. So basically, and if we think back to it, I'm going to go back to the original table here, just so that I remember that the names were sort of down the sides here. So A, B, C, and D, I'm going to just write on this final table A, B, C, and D to remind me of the people that they represented. Andrew, who was it? Andrew, Brian, Christine, Diana. Job 1, 2, 3, 4 was across the top. So 1, 2, 3, 4. And the zeros are the important thing. So again, try to keep using different colors. So these zeros here in the rows are kind of showing the jobs that we could give to different people. So for example, we could give Andrew job 1, 2, or 3. We could give Brian job 2 or 3. We could give Christine job 4. We could give Diana job 1, right? So what you tend to do is the people who just have 1 0 in their row, well, then you allocate that, because that's just saying, like Christine's just saying the only one we can give her is job 4. So we kind of lock that in, all right? Diana, the only one we can give her, or the only one we should give her is job 4. Job 1. So we lock that in, all right? And now what's left is to allocate jobs 2 and 3 to Andrew and Brian. And these zeros here are actually showing us that we could do it either way around. And if you can actually do it either way around, then you just pick one, doesn't really matter which one. So for example, we could give job 2 to Andrew and job 3 to Brian, or we could do that the other way around. We could give job 2 to Brian and job 3 to Andrew, right? As long as each person gets one job only and each job gets done, then we're fine. So I'm just gonna say, let's pick it at random. Brian can have job 2, Andrew can have job 3. Okay, so that would be showing the allocation there. And as it said in the steps there, you don't have to all the time, but you can actually set it up as a bipartite graph if that helps you visualize it. So A, B, C, D, 1, 2, 3, 4. Using the zeros, well, we could say, I'll do this in pencil actually. So we could say, well, the zeros said that Andrew could do 1, 2, or 3. So that Brian could do could do 2 or 3. It said that Christine could do job 4. And Diane could do job 1. Right, and so what we decided from that was that, okay, well, since Diane can only just do job 1, we're gonna lock that one in. Since Christine can just do job 4, we locked that one in. And then both Andrew and Brian could do either job 2 or job 3. So we just picked it. We just said Andrew's gonna do job 3 and Brian's gonna do job 2. So if you find it helpful, this sort of bipartite graph is another way to help with that allocation at the end, but you can just do it straight from the zeros in the matrix, okay? And then it's important to answer the question, all right? So let's go back to the actual question to check what we're asked to do. It said, which job should be completed by each worker to ensure the total cost is kept to a minimum? Well, using our answers there, we said, Andrew, job 3, Brian, job 2, Christine was job 4, and Diana was job 1. Isn't it wonderful that these people's names were A, B, C, and D just coincidentally? Oh, sorry, you couldn't see me writing that. Wasn't very good. All right, so we've answered the question there. And this is really important. I mean, it's always really important to read the question and make sure you've answered it, but especially in these sorts of questions, because sometimes you'll get asked to work out the cost. Other times you might just say who should do which job. So read it carefully and make sure you've answered the question correctly. In this case, it just said who does what job, so that's the answer. If we had to work out the cost, then what you would do is actually go back to the original table and say, okay, well, we've given Andrew job 3, we've given Brian job 2, we've given Christine job 4, and Diana job 1, and we just add those 4 values together if it said to find the total cost.